Hi, welcome to part 2, where we talk about conservative and non-conservative forces. In the last video, part 1, we solved part A of this question. Well, in fact, we did not finish part A. Well, we proved that force number 1 is conservative. So that's an important step. And we explained the meaning of a conservative force. Now, since the force F1, so it's F1 is conservative, then we know that we can associate potential energy with this force. And the relation between them is the following. Force 1, which is conservative, is minus the gradient operator of the potential energy. Or we can write this equation in a different way, saying that if I move from point A to point B, the change in potential energy, final potential energy minus initial potential energy, is really nothing but minus the work done by the conservative force. We finished that in part 1. So now, in part 2, we're going to now try to calculate the potential energy associated with this force. The way to do it is to calculate work. So let's do that. So let's take three-dimensional coordinate system. Let's call this the x-axis. This is the y-axis, and this is the z-axis. Now let's choose 2 points, A and B. And since we're going to do this in general for any location, let's take the initial location to be the origin. So that's 0, 0, 0. Now we want to move to any arbitrary point in a three-dimensional space. So let's say this point here, which has coordinates x, y, and z. And now let's try to calculate the work done by the force. In general, calculating the work means we have first to define or to use a line or a path connecting initial point to final point. Now, since the force is conservative, then the work is independent of which path you take. Because of that, I'm going to use the simplest path. In my opinion, the simplest path is the following. I'm going to start from the origin, the beginning. I'm going to move on the x-axis until I hit the point with coordinate x, which is the same as the final location or coordinate x that I want to reach. So this means this point I reached here has the coordinates x, 0, 0. Next, I'm going to move parallel to the y-axis until I hit this point, which has the same y coordinate as the final point. So this means this point is going to have the coordinates x, same as the initial, because that's a constant x, y, and 0. So we are moving really on the xy plane. Once I reach this point, finally, I'm going to go up, straight up, because the final point is really directly above my location on the xy plane. So I'm going to go straight up to reach the final point. So this is my path I'm going to take. I'm going to start from the origin, move along the first segment, then I'm going to move on the second segment, and finally I'm going to go up on the third segment to reach the final location. Using this path, which is, in my opinion, it's an easy path. Of course, you can choose different paths. I can try another path and calculate the work. So let's try to find the work of this force. Now the work is simply I have a force, which is in this case force number 1, dot a small displacement on this path. So I'm going to cut this path into small displacements, and then I'm going to do a dot product between the two vectors, and then I'm going to integrate from the initial point, which is 0, 0, 0, the origin, until I reach the final location, which has these coordinates. Now this is simply, it's a dot product between two vectors. So this is going to be the x component of force number 1 times dx. Now what is the component of force number 1? It's just 2x. So I'm going to get 2x dx. That's the first component times, so it's F1x, the first component of the force, times dx. Next, the other component will be the y component of the force, dy. Let's go up and check what is the y component. It is simply minus 2yz. So minus 2yz, and that will be dy. The last component of the force, which is y minus y squared. So it's minus y squared dz. So I'm going to do this integration from initial location to final location. Students have to be very careful about this calculation, because when we do, for example, look at the second integration, we are integrating over y, but if you look inside the integral, you have z, and as we move, z will change. So z is not constant really in general, it's a variable. So we have to be very careful in calculating these integrals. Now, of course, we have to check our chosen path and calculate this integral using the path. So let's try to think now how to find this work along this path. If you think about the first segment first, the first segment we are moving on the x-axis. So x is the only variables that gonna change, while y and z are constants and equal to 0. So the first segment, I have only the integration over x that's gonna contribute, which is 2x dx. That's it. That's for the first segment. And the integration will be from x starting from the origin, so that's x equals 0, to the final value, which is x. That's the integration over the first part of the path. Now the second segment, we are moving along or parallel to the y direction. So y is the only variable that's changed, while x is constant, equal to x, and z is constant, which is equal to 0. So now, for the second integration, I got minus here 2. Now, even though I have y as a variable, but z is 0, because we are moving with constant z, which is equal to 0. So now you can see that the second integration over the second segment will not contribute. Finally, I will have the last integral, which will contribute when we move along the last segment going up. So that's we are moving along the z-axis, while x and y will stay constants. So the last part of the integration will be minus. Now notice that y squared is going to be constant on this path, and I'm going to integrate over dz, and we're going to start from z equals 0. That's from down the xy plane to the final location, which has coordinates z, while y is constant. Let's perform the integration, a very simple integration. This is going to give us x squared. The second integration, as we said, is 0. The last integration will be minus. Now notice that y squared is just constant, and integration of dz is just z, and that's it. So this is the work done by the force. Now let's connect things. So potential energy at the end, that's point B, minus potential energy at the beginning, that's point A, is related to the work. So let's try that. So potential energy at the end minus potential energy at the beginning is minus the work. So that's minus x squared plus y squared z. So this is the result of the potential energy. We can move one step forward, and usually, because as we explained in the last video, that what is really physical is the difference in potential energy, not the absolute value of potential energy. And that's why it's customary to do the following. So let's say that the original point we started from is the origin. That's point A. So let's define the potential at A to be 0. Just we set it to be 0. And then the final potential energy at a very general location, that's U, let's just call it now U, is equal to the expression that we calculated, which is minus x squared plus y squared z. So this is the potential energy at any location we are interested in. Notice that at the origin, the potential will be 0. That's what's called the reference point. So point A, we'll just call it, it's a reference point where we measure potential energy relative to that reference point. So that's how we calculate the potential energy. We can check our calculation. One way, an easy way to check your calculation is correct, is to know that the force is supposed to be minus the gradient of the potential energy. So let's check that we should get back the same force we started with. So that's equal the gradient, that's a minus sign. Now the gradient is very simple operator to find. It is the partial derivative of x with respect, it's the partial derivative of the potential energy with respect to x, and that will be the x component of the gradient. So we're gonna get partial u partial x. Now for the y component, it's gonna be partial y partial partial u partial y, and the last component is gonna be partial u partial z. Let's check, perform the calculation, and that should equal minus I unit vector. Now partial u partial x is just minus 2x. So I'm going to get minus 2x. The y component will be partial u partial y. Now we got 2yz, so I'm going to get 2yz. Finally, the last component is going to be partial u partial z, which is simply y squared. So that's supposed to be the force. Now let's check, is this the correct force that we started with? So we got 2x, that's the x component, and then minus 2yz, and finally the last component is minus y squared. Is this correct? Yes, it is. So that's exactly force number 1 in the question. So we are done with the first part of the question. I will leave part B of the question to the next video coming soon. Thank you for watching. See you in the next video.